Hi friends, in this video we are going to learn about canonical form or normal form. So here I will explain how to convert the quadratic form into the canonical form, or we can say the normal form, by using orthogonal transformation x equal to p. What is meant by p and x and y I will explain. So here I will just remind what is meant by quadratic form. Let's say here q equal to here summation I running from 1 to n summation j running from here 1 to n a I j x I x j, where a I j is same as here a j I. So here this is the quadratic form in n variable. So here how to write for two cases. For example, I want to write, let's say, quadratic form in two variable. So here I will write q2 of x, which is equal to, how to write quadratic form in two variable. Let's say here a11 a12 a21 and a22. So here write a11 x1. Here corresponding to this one, here let's say this is 1 and this is 2. So here corresponding to 1, let's say x is the unknown. Corresponding to 2, let's say x2 is the unknown. Here this is a11. So right here x1 x1. So x1 square plus a12. Here this is a12. Here x1 and x2. But here aij is same as aj. a12 is same as a21. So here if a12 is same as a21, so here I am writing 2 times here a12 x1 x2 plus a22 and x2 square. So here this is the quadratic form in two variable. So here now in the same way, how to write the quadratic form in three variable. Let's say q3 of x. So here which is equal to a11 x1 square plus 2 times a12 x1 x2 plus 3 means third case is here 2 times a13 is same as a31, that's why 2 times x1 x3. So x1 x3 here plus a13 is over here. For example, this is a11 a12 a13, here a21 a22 a23, this is a31 a32 a33. So here a11 x1 square, here a12 is same as a21, that's why here I am writing 2 times a12 x1 x2 plus a13 is same as a31, 2 times a13 x1 x3 plus, now come to here, this is covered with this, here plus here a22 x2 square plus, come to here a23, this is a23, here a23 is same as a32, so here 2 times a23 x2 and this is x3. So here this is the quadratic form in three variable. In this way you can write for any number, that is you can write for 4 variable x1 x2 x3 x4, or you can write for 5 variable also. But here what is meant by quadratic form? Let's say q equal to x transpose ax. Here this is same as this. Here if I open this, which is same as, here I got summation I running from 1 to n, j running from 1 to n, a I j x I and xj. So here which is I got same thing. So after solving this, here this is my quadratic form in n variable. Now, so what is meant by normal form? Let x equal to p y, be an orthogonal. So orthogonal transformation. So transformation which transform q to summation lambda, here q2 summation lambda I y I square I running from 1 to n as here let q equal to x transpose x, which is equal to summation I running from 1 to n, summation j running from 1 to here n aij xi xj where here Aij is same as Aji. So here where Aij is same as Aji. So here let x equal to py be an orthogonal transformation which transform q, means this whole q, to summation I running from 1 to n lambda I yi square as. So here just put x equal to py in place of this. Therefore here q equal to, here x transpose means p y transpose, here this is a, this is py, which is equal to, since suppose for example this is A1 matrix, this is B is the matrix, then AB transpose is same as B transpose A transpose. Here use this property, so from here, so here py transpose, so is same as y transpose p transpose, this is A, this is p, and this is y. So here, so this is equal to, so which is equal to, here I am writing this p transpose AP as d. So here y transpose d, and this is y, where d equal to p transpose AP is a diagonal matrix having diagonal elements are the eigenvalues of A. So here let q equal to x transpose AP, this is the quadratic form in n variable, and let x equal to py be an orthogonal transformation which transform your q to this summation I running from 1 to n lambda I yi square as, so this. So here how, so here I am saying this q is transformed into this. So how this q is transformed into this? Here this y is column vector y1 y2 yn. Here this y transpose is row vector y1 y2 up to y3, and here this d is the diagonal matrix. What is meant by diagonal matrix? Matrix in which all the non-diagonal entries are 0, that is diagonal matrix, and diagonal entries are the eigenvalues of this matrix A. So here this is matrix A. So here I will write the same thing over here. So here I will write the same thing over here. So here q equal to, here this is y1 y2 up to yn. So here now d is the diagonal matrix, therefore lambda 1 0 dash up to 0. Here 0 diagonal entries lambda 2 eigenvalue, here 0 dash up to 0. So in this way here 0 dash up to lambda n. So here lambda 1 lambda 2 lambda 3 up to lambda n are the eigenvalue of the matrix A, and this is equal to, here this is equal to y1 y2 up to yn. So here you can solve these things. Here you can solve this matrix multiplication. You will get lambda 1 y1 square plus lambda 2 y2 square plus dash up to plus lambda n yn square. So which is same as summation lambda I yi square, summation I running from 1 to n. So that's why here I said this q transform, here this q transform to summation I running from lambda I yi square. This is called the normal form of the quadratic. Here this is called the either the normal form or canonical form, or some author said this is the square form. So here in your square form, let's say this is your square form, q equal to lambda 1 y1 square lambda 2 y2 square plus dash up to lambda n yn square. Here this in your quadratic, in your normal form or canonical form or square form. So here this lambda 1 is the eigenvalue 1, lambda 2 is the eigenvalue here, and so on, lambda n is the eigenvalue of this matrix D. So here of this matrix A, here this is written as D as a diagonal matrix having all the diagonal entries are the eigenvalues of this matrix A and non-diagonal entries are 0. now here I am saying this here this is the quadratic form. In your quadratic form, here q equal to x transpose x, here cross terms are available. That is, for example, this is the quadratic form in two variable. So here a11 x1 square plus 2 times a12 x1 x2 plus a22 x2 square. But here in this quadratic form, here cross term, that is 1 2 position and 2 1 position is available. But here in your normal form, cross positions are 0. Here so here, for example, in this quadratic form in 3 variable, you can observe this 1 2 position is available, 1 3 position is available, and this way 2 3 position is also available. But in quadratic form in 3 variable, that is normal form in 3 variable, cross terms are vanishing, that is diminished. So here this is the normal form or canonical form or square form of the quadratic form. So which is transformed by here x equal to p by, that is orthogonal transformation. So here how to, so based on this normal form or canonical form, so I want to define the nature or value class of the quadratic form by q to this square form, normal form, canonical form with the help of this x equal to py. So here I will define one by one. So this is equal to, here again I will write q equal to summation I running from 1 to n lambda I yi square. So here this is the quadratic form. Here you can observe one thing. So this is equal to, for example, for in 3 cases. So here I want to write the nature. So here value class. So here first I will define the index. Here what is meant by index? Here index means, so what is meant by index? Here this is the normal form. Number of positive term in the quadratic form is the index. So for example, so here this is the lambda I. Here lambda is the eigenvalue and yi is the unknown, y1 y2 up to yn. Here I is running from 1 to n. Now whether this first term, so here I will open. So here this is the square form. So first write this here. Here this is the eigenvalue and this is the yi square. Whether y1 is positive or negative, this y1 square is always positive. In the same way y2 square is always positive. In the same way yn square is always positive. Here let's say this is my first term. Here this is my second term, and so this is my nth term. First term, second term, nth term. Whether this first term is positive or negative, it is completely based on this eigenvalue lambda 1. Here this is the second term, whether it is positive or negative, that is completely based on this eigenvalue lambda 2. So in the same way, this is the n term of the normal form. So whether this is either this term is positive or negative, it is completely based on, here it depends on eigenvalue lambda n. So here for example, if lambda 1 is here, if lambda 1 is positive, that is strictly greater than 0, and lambda 2 is positive, strictly greater than 0, in this way up to lambda n is strictly greater than 0. So here all the terms are positive. So here index means number of positive term in the normal form. That is, here I will define index equal to, here index is here, which index equal to here number of positive term in canonical form. Number of positive term in canonical form. So here number of positive term in canonical form is same as number of positive eigenvalue. So here if eigenvalue lambda 1 is positive, then this term is positive. Eigenvalue lambda 2 is positive, then this term is positive. In the same way, eigenvalue lambda n is positive, then this term is positive. So that's why here can I say this is equal to number of positive eigenvalue. of A corresponding to the quadratic form Q. So here this is the A matrix, here this is the coefficient matrix A corresponding to the quadratic form Q. So here this is my index. So here either index number of positive term in canonical form or normal form or square form. This is same as here. So it is denoted by P. Here index is denoted by P. P equal to index equal to this. So therefore again P equal to number of positive eigenvalues of A, where A is the coefficient matrix corresponding to the quadratic form Q. Now second thing, what is meant by rank of the quadratic form? Here let's say Q equal to, here I am writing Q equal to X transpose AX. Here rank of the quadratic form is same as, here I will define rank. Here rank of the quadratic form is equal to number of non-zero term. So you can say number of non-zero term, or you can say number of non-zero eigenvalues of A. So here number of non-zero eigenvalues of A, that is my rank. So it is denoted by R. So here I will denote this as, here R equal to rank of the quadratic form equal to number of non-zero eigenvalues of E. So here third thing, so what is meant by signature? So here since number of non-zero eigenvalues is R, so number of non-zero eigenvalues is R and number of positive eigenvalues is P. Here R is the number of non-zero eigenvalue, means positive as well as negative eigenvalue, and this P is the number of positive eigenvalue. So here I am subtracting number of positive eigenvalue from total eigenvalue, positive as well as negative. Then the R minus P is the number of negative eigenvalue of A. So here number of negative eigenvalues of A. Then here this is R minus P is the number of negative eigenvalues. Then fourth I will define what is meant by signature. So here signature is nothing but, here signature equal to number of positive eigenvalue minus number of negative eigenvalue, means the difference between number of positive eigenvalue and negative eigenvalue. So signature is same as, here the difference between number of positive eigenvalue and number of negative eigenvalue, that is n minus p. So which is equal to, here which is equal to p minus r plus p, which is equal to 2p minus r. This is my signature. Here where p is the index and r is the rank of the quadratic form. Here signature is difference between positive term and negative term of the canonical form. So here this is my signature. So here Q equal to X transpose X be the quadratic form, is the quadratic form, and X equal to P Y be the orthogonal transformation. Here orthogonal transformation. Then Q transform this Q transform Q to, here Y D, Y transpose D Y, which is the normal form. Here which is the normal form, that is Q equal to, here Q equal to X transpose X becomes Q equal to summation lambda I Y I square I running from 1 to n. So this is my normal form. Based on this normal form, here I am defining index. Number of positive term in the quadratic form is my number of positive term in the normal form is my index. Here number of positive term in the canonical form. Here this term is positive, means this eigenvalue is positive. This second term is positive, means this eigenvalue lambda is positive. This nth term is positive, means this eigenvalue lambda n is positive. That's why number of, here p is same as number of positive eigenvalues of A. Here index I am defining in terms of number of positive terms and in terms of eigenvalues. So here this is my index, this is my rank. Here rank of the quadratic form is number of non-zero eigenvalues of A, and R minus P. Here P is the number of positive term and R minus P is the number of negative eigenvalues of A. So here P is the number of positive eigenvalues here and R is the non-zero eigenvalues, all collection of all non-zero eigenvalues, positive as well as negative. Then R minus P is the negative eigenvalue and signature is the difference between positive and negative. So here this is P minus R minus P is here minus minus plus R plus P, 2P minus R, that is the signature. Now so based on this whether all the eigenvalues are positive, negative, 0 and all are negative, I will define the nature of the quadratic form or value class of the quadratic form. So here I will define what is meant by so now I want to define value class or nature of the quadratic form. So I want to define nature, or we can say here, or value class of quadratic form. Here let Q equal to, so X transpose AX, and here this is the quadratic form in n variable x1, x2, xn. So we transform this quadratic form into normal form by here Q equal to, so here I am transforming I running from 1 to n, here lambda 1 y 1 square. So here this is the either square form, or here this is equal to, here I will write this is equal to lambda 1 y1 square plus lambda 2 y2 square plus that is up to plus lambda n y n square. So here this is the quadratic form in n variable, this is the normal form or canonical form in n variable y1 y2 up to yn. So here in this quadratic form, so this is my coefficient matrix corresponding to the quadratic form X transpose Ax. So here let's say this is my coefficient matrix, let's say A, having so n row and n columns. So this matrix has n eigenvalue lambda 1, lambda 2 up to lambda n. So here if all the eigenvalues are positive, if lambda 1 is positive, this is the positive term, since y1 square is always positive. If lambda 1 is positive, so this whole term is positive. If lambda 2 is positive, then the second term is positive. If lambda n is positive, this nth term is positive in my normal form. So here in my quadratic form, first eigenvalue is positive. So in my normal form, first term is positive. Second eigenvalue is positive of this quadratic form, then the second term in the normal form is positive, and so on. So here in this way, if the nth eigenvalue is positive, so here this is the n term is positive. So here what is meant by positive definite, and so here I will define positive definite here, positive definite. When we say that the quadratic form, here this quadratic form is positive definite. Here if all the eigenvalues, let's say if all the lambda I, here I will write in terms of symbolic, here if all lambda I, that is eigenvalues of this Q of quadratic form Q, here quadratic form Q are positive, then quadratic form is positive definite. So then quadratic form is positive definite. Here I am saying lambda 1, lambda 2, lambda 3 up to lambda n, all the eigenvalues are positive, then the quadratic form is positive definite. So here if lambda 1 is positive, lambda 2 is positive, and so on, lambda n is positive, then the normal form becomes here, therefore normal form so becomes Q equal to, here lambda 1 summation y I square. So here lambda 1 positive, lambda 2 positive, so if all the terms are positive, then their summation is positive. So here now what is the relation between P, R and N? So here if all the eigenvalues are positive, means all the terms are positive. Then here p equal to, how many terms are here? N terms. P equal to n. So here all the terms are positive, means here r is the number of non-zero eigenvalues here, which is equal to r. So here this is the relation between p n r. Now here I will write. So in terms of here, same here, r is equal to here. Sorry, p equal to r, which is equal to n. Same. So here now second term. So here all terms are positive. That's why this is positive definite. Now here if all the lambda are positive and at least one lambda eigenvalue is 0, then the quadratic form is positive semi-definite. What is meant by positive? Here positive semi-definite. So here I will define the definition. If at least one eigenvalue is 0 and all the remaining eigenvalues are positive. Here if at least one eigenvalue is here, one eigenvalue is 0 and remaining all remaining all eigenvalues are positive, then quadratic form is positive semi definite, PSD. Here positive semi definite, here I will write positive semi definite. Here if at least one eigen, here let's say we have n eigenvalue and out of n at least one, let's say lambda 1 is 0 and remaining lambda 2, lambda 3 up to lambda n are positive, or we can say lambda 2 is 0 and lambda 1, lambda 3 up to lambda n are positive, or we can say lambda n is 0 and lambda 1, lambda 2 up to lambda n minus 1 are positive. Here I am saying at least one is positive and remaining all the eigenvalues are positive. Then the quadratic form is positive semi-definite quadratic form. So here in this case also, for example, let's say here then normal form becomes here normal form becomes q equal to, let's say, summation I running from 1 to n, here lambda I y I square is always strictly greater than 0. So here for example, let's say nth term is 0, let's say nth eigenvalue is 0. So here this is positive and so on. This is lambda n minus 1 y n minus 1 square, this is positive. So here last term is 0, so here remaining all are positive, that's why this whole term is positive. Now in this case, what is the relation between p, r and n? So here all the eigenvalues are positive, so except one. So here I am taking at least one. Let's say one eigenvalue is 0. So for the sake of understanding, so here all the eigenvalues are positive. Then this means that p equal to, and r is the number of non-zero eigenvalues. So here and p is the positive terms, or you can say the positive eigenvalue. Can I write p equal to r? Yes. So here and n is the number of eigenvalues. So here n is the number of eigenvalues. In n you can take positive eigenvalue 0 and along with here positive eigenvalue, negative eigenvalue and 0 eigenvalue. Here p is the only positive eigenvalue and r is number of non-zero eigenvalues. Here all the eigenvalues are non-zero and they are positive. So here all the eigenvalues are positive and non-zero and one eigenvalue is 0. So that's why can I write p equal to r, which is less than n. So here for example in case of 4 I will prove this relation. Here let's say 2x1 square plus 3x2 square plus 4x3 square plus 0x4 square. Here this is the quadratic form in 4 variable x1, x2, x3, x4. Here at least one eigenvalue is 0. So here lambda 4 corresponding to this x4 eigenvalue is 0 and remaining eigenvalues are positive 2, 3, 4. Here p is the number of positive p is the number of positive term. Can I take 3? Here r is the number of non-zero eigenvalue. Here this is non-zero, this is non-zero, this is non-zero. So can I take r equal to 3? Yes. And n is the number of eigenvalues. So n is the number of unknown. Number of unknown is same as number of unknown. So if you have 4 unknown, you will get 4 eigenvalue. So here 1, 2, 3, 4. Here this is 2 is one eigenvalue, 3 is one eigenvalue, 4 is one eigenvalue, and 0 is another eigenvalue. So which is equal to 4. So 3 equal to 3, which is strictly less than 4. So here p equal to r, which is strictly less than n. So that is the relation. So here this is the relation between Pn and R in terms of positive semi-definite. Now I want to define negative definite. Here in negative definite means all the eigenvalues are negative, then the quadratic form is negative definite. Here I will define the negative definite quadratic form. Here so here what is meant by negative definite? Here negative definite. So here if negative definite, if all the eigenvalues are negative, if all eigenvalues are negative, then quadratic form is negative definite. Here now observe one thing. Here if all the eigenvalues are negative, then the quadratic form is negative definite. Here corresponding to this quadratic form, if all the eigenvalues are negative, then this quadratic form is negative definite. Then if all the eigenvalues are negative, then normal form becomes normal form q equal to, here if lambda 1 is negative, that is, so this is minus with lambda 1. If lambda 2 is negative, so minus with lambda 2. Let's say lambda 1 is minus 1, lambda 2 is minus 2, lambda 3 is minus 4. In this way lambda is let's say minus 100. So for example, if you have 100 eigenvalue, so here this is negative term, this is negative term, and so on, this is negative term. So can I write this is same as minus times here I running from 1 to n. So here lambda I yi square. So here which is strictly less than 0. Now I want to define. So here if all the eigenvalues are negative, this is the quadratic, this is the normal form. So here normal form is minus times summation I running from 1 to n lambda I yi square minus that is less than 0. So that is negative term. Now so what is the relation between p and r? Here all the eigenvalues are negative. So lambda 1, lambda 2, lambda 3 up to lambda n. So here this means all the eigenvalues are negative. This means p equal to simply 0. Here p is the number of positive eigenvalue, or we can say p is the number of positive term. Here lambda 1 y1 square is negative term, lambda 2 y2 square is negative term. In this way lambda n yn square is also negative term. This means that lambda 1 is negative, lambda 2 is negative, and lambda n is negative. So here p is 0. So here in this case p is 0 and r is the number of non-zero eigenvalue. So here lambda 1 is non-zero, that is negative but non-zero, lambda 2 is negative but non-zero, and so on. Lambda n is negative but non-zero. So can I write r equal to here n? So here p equal to 0 and r equal to n. This is the relation between p, r and n in terms of negative definite. Now I want to define negative semi-definite. Here in the negative semi-definite, if here in the same way like positive semi-definite, if at least one of the eigenvalue is 0 and all the other remaining eigenvalues are negative. Here I will define negative semi-definite. Negative semi-definite. Here if at least one eigenvalue, one eigenvalue is 0 and remaining all eigenvalues are negative, then quadratic form is negative definite, negative semi definite. Then quadratic form is negative semi definite. Now here all the eigenvalues are negative and at least one eigenvalue is 0. So here then normal form becomes q equal to here summation I running from 1 to n lambda I y I square, which is again strictly less than 0. So here y is again strictly less than 0. So here at least one is 0 and all the remaining are negative. For example, can I write here q equal to, here I will write in terms of same, minus 2x1 square minus 3x2 square minus 4x3 square, here minus, here plus 0x4 square. Let's say this is the quadratic form in 4 unknown, x1, x2, x3, x4. So 4 unknown means 4 eigenvalue, minus 2, minus 3, minus 4, 0 are the eigenvalues of this quadratic form. But here lambda 1 is negative, lambda 2 is negative, lambda 3 is negative. This is 0 times x4 square. Can I write this is, here this is minus term, this is minus term, this is minus term, this is 0 term, no effect. So this is less than 0. So this is less than 0, q equal to. So here what is the relation between q, p, r, p and n? Here p is the number of positive term. So can I take here number of positive term in this are 0. So here this is equal to p equal to 0. P is the number of positive term, or we can say number of positive eigenvalue. So all are 0. So here r equal to number of non-zero eigenvalue. Can I take r equal to, so n, same relation here also. Now so this is positive definite, positive semi definite, negative definite, and this is negative semi definite. Now what happens when some eigenvalues are positive and some eigenvalues are negative? If the quadratic form having some eigenvalues are positive and some eigenvalues are negative, then that quadratic form is the indefinite quadratic form. So here I will write here. So here if indefinite quadratic form, here indefinite quadratic form, here if some eigenvalues are positive, here if some eigenvalue are positive and some eigenvalue are negative, then quadratic form is indefinite. So quadratic form is indefinite. So for example, let's say q equal to 2x1 square plus 3x2 square plus, let's say, minus 3x3 square minus 5x4 square. So here this 2 and 3 are the positive eigenvalue and this minus 3 and minus 5 are the negative eigenvalue. So here in this quadratic form, positive as well as negative eigenvalues are there. That's why this quadratic form is the indefinite quadratic form. So here in this way you can define the value class or nature of the quadratic form based on the eigenvalues. So here in this way you can define. So one way is based on the one way of define the nature of the quadratic form is based on the leading principal minor. So here one way is leading principal minor. How to define the nature of the quadratic form? By using the leading principal minor. So here we have defined by using the eigenvalue. Let's say here let q equal to x transpose Ax with the quadratic form, and here A equal to, here is the coefficient matrix, here A11, A12 up to A1n, here A21, A22 up to A2n. So here I will write, just for understanding purpose, here I will write 4 cross 4 matrix, A12, A13, A14, here A23, A24, A31, A32, A33, A34, A41, A42, A43, A44. Let's say this is the matrix corresponding to this quadratic form x in 4 unknown. That is here 4 variable. Let's say 4 variable. So x1, x2 up to x1, x2, x3 up to x4. So here the leading principal minus starting from A11 is here the leading principal minor starting from A11 of order 1, 2, 3, 4 are. Here the leading principal minors starting from A11 means always start with A1. So R, here I will of order 1, here I will write D1. So order 2 write D2 and so on. This is equal to principal minor of A11, that is determinant of A11. Here starting with A11 principal minor of order 2, that is here start with A11 of order 1. So this is simple A11. Start with A11 of order 2. A11, so this A11, A11, A12, A21, A22. So here start with A11 of order 3, that is here D33. So here A11, A12, A13, A21, A22, A23. This is A31, A32, A33. So here start with A1 of order 4, which 4? So here start with, here I will write here D4. Start with A1, 1, A1, 2, A1, 3, A1, 4, A2, 1, A2, 2, A2, 3, A2, 4, A3, 1, A3, 2, A3, 3, A3, 4, A4, 1, A4, 2, A4, 3, A4, 4. Here this is the quadratic form in 4 variable, and this is the matrix corresponding to this quadratic form. The leading principal minors starting from A11 of order 1 is this one, of order 2 is this one, of order 3 is this one, and of order 4 is, so of order 4 is this one. So here based on this D1, D2, D3, D4 sign, so here I want to define the nature and value class of the quadratic form. So here nature, so nature. So here if all di, here if all the di, that is if all, that is if D1 is positive, D2 is positive, D3 is positive, and D4 is positive. Here if D1, D2, D3, D4 are positive, then the quadratic form is positive definite. Here then quadratic form is positive definite. So one. Second, if at least one di is 0. So here say here if at least one di, say d1 is 0 and remaining, here say here if at least one di is 0, say if at least one di is 0, say d1 equal to 0, just for understanding, and remaining di are not 0, that is d2 is not 0, so d2 is non-zero, so here and remaining di are strictly greater than 0, that is here d2, here d2 is strictly greater than 0, d3 is strictly greater than 0, and d4 is strictly greater than 0. Here just at least one, any, here I am taking just d1, so if you can take d2 is 0 and d1 d3 d4 is non-zero, you can take d3 0 or you can take and d4 is 0. So here at least one di is 0, say d1 is 0 and remaining di are positive, then quadratic form is here positive semi-definite. So if at least here all the di are positive definite, here at least one di is 0 and remaining are positive, then negative, a positive semi-definite. Here third means if all the di, if all di are negative, then quadratic form is negative definite. And fourth, here if all the di are, if at least one di is 0, if at least one di is 0 and remaining di are negative, then quadratic form is negative semi-definite. So here fifth is indefinite. If some di's are positive and some di's are negative, if some di are positive and some di are negative, then quadratic form is indefinite. So here in this way you can say the value class or nature of the quadratic form by using leading principal minor starting from a11 of order 1, 2, 3, 4. Here I am taking 4, you can take 5 cross 5, you can take 6 cross 6, anything. So here in this way, so in this video we have learned about how to convert the given quadratic form into the normal form. So here in the normal form or canonical form, so here lambda 1 y1 square, lambda 2 y2 square up to lambda n yn square, this is either canonical form or we can say normal form, or some author says square form. If all the lambda i's are positive, means each and every term is positive, then that quadratic form is positive definite. If all the eigenvalues are positive and at least one eigenvalue is 0, then the quadratic form is positive semi-definite. If all the eigenvalues are negative, then the quadratic form is negative definite. If all the eigenvalues are negative and at least one eigenvalue is 0, then that quadratic form is negative semi-definite. And some eigenvalues are positive and some eigenvalues are negative, then that quadratic form is indefinite. So here in this way we can define the value class, nature, or the canonical form or normal form of the normal form. So here corresponding to the quadratic form, Q equal to x transpose Ax with respect to the orthogonal transformation x equal to Py. Here P is the model matrix I will define, so while defining the working rule. So thank you.